a lot for organizing this and for giving me the opportunity to talk. Actually, I'm pretty sure I applied for a 15-minute talk, so the organizers were so kind to give me an hour. That's nice. I'll use the full hour. The only trouble is we only really have 15 minutes worth of new results, but perhaps it's not so bad because then chatting with Blaise, we actually came to the idea that maybe I should give also a broader context, not only the most recent results, but like also remind a little bit of what was done in this area and what's the status. So I mean, it will be a research talk. It's not just a review, but it will be a research talk with a log intro, so to say, and I hope that can also be useful. So roughly speaking about what ADS, CFT, or holography can tell us about fermionic systems and what are some new developments in that field. So this is, so the recent work is in collaboration. Okay, so now it stopped working.
Click the PowerPoint once. You've been hijacked by their meeting is recorded.
Okay, right.
You really have to click the PowerPoint once.
Maybe. Okay, now it works. Yeah, so the recent results are in collaboration with Ben from Amsterdam and my student Vladan Getsin, and the old results are mainly with the Leiden group, so with my co-supervisors Jan and Kunrad and other people from Leiden. Now, let's see what is the essence of the Fermi liquid theory. I mean, I'll also talk about Fermi surfaces in general. It's often not even clear if you really have a strict Fermi liquid or not. But I guess the most interesting question is whether we can get a Fermi liquid, because that's kind of the most robust phase that we have in real world materials. And it's something that can be sharply tested. So what would be the essence of a Fermi liquid? Well, I'd say, I mean, the way it's usually posed in textbooks, well, it's some renormalized Fermi gas with weakly interacting quasi-particles. So quasi-particles can be drastically different from bare electrons, but effectively they still have kind of weak interactions that you can encompass through this Landau theory, which arguably is the first effective field theory ever written. So because you really don't suppose anything about the microscopics, you write this kinetic equation which just basically gives you quasi-particle energy in terms of these effective interactions, those Landau coefficients. And these interactions are effectively non-local because they solely depend on K, that is on your place on the Fermi surface. Of course, that's very obvious and expected from condensed matter viewpoint because speed of light is very high, and effectively we can't think of we can just forget the effects of retardation. But then for holographic duals, that will actually bear some interesting consequences. I mean, if you're strict about this, it's not so easy to cut the holographic dual, but that's good on the other hand because it drastically restricts what you could in principle do. So what would be some litmus tests? So the scaling of free energy, then the log violation of the entanglement entropy scaling, the existence of the zero sound mode resistivity. So these would be some like sharp tests that a Fermi liquid should pass, and there certainly can be models which pass some of these, but not all. So that's at least from the theoretical viewpoint, you can be like partially Fermi liquidish and partially not. So so why the wormhole in the title? Well, it's not really like a wormhole. At some point we thought it was. At some point we thought that the gravity dual to a Fermi liquid is really, a wormhole in the bulk. It turns out that it's not, but nevertheless, it does have some of the similar properties, like including the log violation of the entanglement entropy scaling. So there, eventually it should a little bit click together, but in essence, it's like an independent but related project that will come at the very end. So for now, you don't have to think much about wormholes. Now, so the important question is, can a Fermi liquid ever be strongly coupled, which I already discussed with a few people here during the workshop, because even though ADS CFT in principle works everything, it works at all the couplings on both sides, so just a duality between open and closed strings or string theory on ADS spaces and gauge theory. Nevertheless, the case that you're usually interested in and that we have good control over is weakly coupled classical gravity or supergravity in the bulk. which is dual to strongly coupled large N gauge theory, if you want, strongly coupled theory with a large number of colors, large number of different charges of the particles. So that's really what we normally want and what we can compute. So I mean, in that sense, there's definitely no gravity dual for a weakly coupled system. So it's it's important whether it can ever be strongly coupled. And to the best of my knowledge, and from what I gathered, from the literature and also from various discussions in the previous years, I think it's still a controversial question. I'll elaborate a little bit now. But before that, maybe I should answer, so why the hell should we be interested in building a holographic model? Because you could argue, well, Fermi liquids are one thing that you understand well from condensed matter viewpoint. So what's the point then? Well, so, okay, I would say that, the reasons are mainly theoretical, but important. So to understand Fermi liquids within this broader context of Landau mean field reasoning and effective field theory. So just to understand a little bit better how this Landau theory works, because it's a bit of a miracle. It works very well, but only much later, people basically started to lay its foundations logically, starting from some effective action or something. Then also what's interesting is to understand the limits of holography. So basically what can or cannot be packaged in the gravity dual. That's important in general, to understand what we can do. Then condensed matter motivation would be to understand how Fermi liquids form in quantum phase transitions, like in heavy fermions, when you can become Fermi liquidish in this large Fermi surface phase. So that perhaps would be something that is not, that's not trivial to understand from existing, field theory or lattice theory approaches. So basically how you become Fermi liquidish at a phase transition, and then also to generalize and systematize the many microscopic derivations, because it's not one, there are many, as you would expect from an effective theory. Of course, there are various microscopics that can lead to it, but then, so even though holography is not a microscopic theory, but maybe it can just show, what all these approaches have in common. So the history of this approach, so just holographic approach to Fermi surfaces and Fermi liquids. So we started from simple-minded holographic models and got enthusiastic initially because, there were many phenomena which looked like real world, and also some specific predictions, like for oscillations in magnetic fields and for spectralator and so forth. And then, so many people got enthusiastic at first, but then got demoralized because at some point easy problems were exhausted, and it seems like we just hit a brick wall. At some point it became harder and harder either to make some breakthrough from the theory side, like something non-trivially new and different, or also to really connect it to condensed matter systems. And now, so some of us are trying to come back specifically to modeling Fermi surfaces, but in the true spirit of effective field theory. So with no microscopic fermions, and therefore also no fermions in the bulk, but really just effective bosonic fields. So first I'll tell a little bit of the general holographic Fermi liquid and Fermi surface theory or models basically, and what we know so far, including this, so to say, bittersweet history of holographic Fermi surfaces. So basically what was done and what we could never do. Then so I'll talk about this current approach. It's work in progress about holographic Fermi liquids from patch bosonization, and then perhaps if time permits, maybe a little bit about wormhole hydrodynamics. But number 4 I might well skip. Okay, so let's now talk a bit more about the litmus tests and the conditions to be satisfied by a prospective holographic Fermi liquid model. So if you read the original Landau papers from 53, it's 3 papers. So one is just the essence, the dispersion relation, then the second is thermodynamics and heat capacity, and the third is zero sound. So if you read the papers, then it's what you find in every textbook: replace electrons with long-living quasi-electrons or quasi-particles, but there's no microscopy there. So there's there's no discussion of individual electrons or about microscopic interactions or about specific properties of materials or anything. It's really just symmetry-based reasoning, and also general principles of continuity that all the functions change continuously as you turn on the interactions. So it's really, yeah, I mean, not too different from Landau's own mean field theory for like bosonic order parameters. So yeah, what does it look like? Well, so yeah, for free electron gas, we just have, yeah, free dispersion relation, which you can then expand around the Fermi surface, whereas for a quasi-particle liquid, on top of that, you have some, yeah, correction encompassed in this interaction function F. And then, yeah, so the confusing thing, I mean, from a modern theorist viewpoint, is that there's no effective action given by Landau, just this, yeah, kinetic equation. So normally, yeah, so these like collisions among the quasi-particles, they account for the, yeah, for the correction in energies. And now there are some people writing effective actions, but that requires some fancy maths, cohomologies, and so forth. So there are papers by Luca della Creta about that, and there are many others, but basically it's not so easy to actually write this. And to this day, as we know, it works great, but yeah, we still find surprises when we try to understand it really well. Okay, so yeah, the first perverse thing, I mean, really unclear to me, as I said, is whether, yeah, it can be strongly coupled or it's always weakly coupled, because on one hand, these quasi-particles can be very strongly renormalized, like a factor of 100 in heavy fermion systems, a factor of 1,000 in helium-3, but on the other hand, so in this case, the classical gravity dual would exist, but on the other hand, so quasi-particle interactions are always perturbative. And so from this viewpoint, there should be no classical gravity dual at all. Then the second weird thing is symmetry. So yeah, there's talk about Fermi surface rigidity, so-called, which is kind of equivalent to saying that it's protected by some sort of symmetry. So yeah, it's mentioned in the famous Anderson book. Then also, I mean, Jan would often talk about this, and he has it in his, yeah, like textbook of condensed matter. So yeah, the Fermi surface in a sense is like an order parameter, but it's not clear what is the symmetry that it breaks. Now, if you think a bit, so yeah, at every point you have like, at every single point of the Fermi surface, you have basically U1 symmetry, because in every scattering event, you have like charge conservation. So in that sense, it's kind of local U1 symmetry, but it's not in the usual sense of local symmetry in the sense of gauge symmetries, because you cannot gauge it. A gauge symmetry can be gauged, you do a gauge transformation. Here you cannot, it's just that if, say, if material is 2D and the Fermi surface is circular, then it's just at every point of the circle, you have this U1. So it's rather U1 to the power of infinity. So like a continuum of points, each of them exhibiting U1 symmetry. And that's discussed, yeah, in this short, like three-page note by Anderson and Haldane, and also in later papers by Haldane. And the more modern and more precise formulation is by Dominique Els and Sandhill. So this is made precise in terms of this loop group, LU1, which is basically U1 to the power of infinity, but kind of quotient U1, because there's also this global charge conservation. That's what it means, that, okay, at every point you have U1, but then, I mean, any possible scattering events anywhere on the Fermi surface is also subject to constraint that the total charge on the whole integrated over the whole Fermi surface should be conserved, and that's why it behaves like this. I mean, strictly speaking, even this, I mean, it's not really an equality. There are subtleties about representations, but I don't think that's important for us now. And also, yeah, in this Anderson and Haldane paper, it's argued to be kind of quantum critical point at t equals 0. Frankly, I didn't really understand the argument. I mean, it's a paper with maybe 1 or 2 equations. I mean, it's mainly their thoughts about this. I didn't understand why they claim it to be a quantum critical point at t equals 0, but this will be useful later on, because the holographic model that I want to propose now is actually a CFT, or a quantum critical point, at every point of the Fermi surface, or at every patch. But then, since patches interact all together, then, I mean, this spoils conformality as should be expected, because if you're quantum critical, there are no quasi-particles. So this has to be broken somehow. But there is perhaps some notion of, something quantum critical. Okay, let's see. So what we know about holographic modeling so far.
Can I ask a question?
Mm-hmm.
If you go back, you were saying, on the previous slide, that the difference between the Fermi gas and the Fermi liquid is the presence of Landau interactions between the quasi-particles.
Yes.
So that doesn't seem to affect this symmetry, this emergent symmetry of the Fermi surface. Isn't that a little disconcerting? Because the presence of these Landau interactions, they're crucial to getting, say, zero sound. They seem to be an important part of the phenomenology that we're after.
Oh, right. Okay. You mean, yeah, how would this change for a non-interacting gas? Okay. Yeah, good point. Okay, let me see. Yeah, u1 to the power of infinity is true. Well, I'm not sure. I have to think about it, but I think that the difference is that for a free Fermi gas, you really get just u1 to the point of infinity, because then there are no scattering events and there's no quotient to take. So, I mean, the total charge is trivially conserved simply because, I mean, it stays the same at every point. So, I'm not 100% sure, but I think that, yeah, in that case, I mean, it's a little bit different. It's not LU1, it's literally just U1 at every point because there's nothing happening. I mean, at every single point.
The total charge is always conserved. Whatever we do, whether they are other interactions or not.
Yeah.
Question is whether the local charge on each patch of the Fermi surface, and that is now broken by the presence of Landau interactions.
Yeah. So yeah, but it should still. Yeah, but every scattering event, like, yeah, still preserves. Yeah, still preserve the charge. I mean, on the whole surface. So
I'm also a little bit confused by the fact that these Landau interactions, they're really all just thermodynamics, right? They're not in the collision kernel. They're static.
Okay, yeah. You mean, but how does that affect the symmetries? Or
I'm confused about how something that I would more naturally think of in terms of corrections to thermodynamics would relax the charge at every point on the Fermi surface.
No, but they're also in the, I mean, they're also in the kinetic equation. I mean, right? I mean, you have quasi-particle collisions and that will influence the dispersion relation. So they're there in equations of motion.
They're not sitting on the right-hand side in the collision kernel. They're sitting on the left-hand side.
Oh, okay,
Corrections to the energy. That smells like more what we think of as hydrostatic derivative corrections, for instance, in hydro.
Okay, so you would expect them, you mean not to show up at all in the action, but
Anyhow.
Yeah, I don't know. I would still think that, I mean, also, I mean, if they're in the free energy, they should be in the action somehow, just that.
Sure.
Yeah. Yeah, but for the symmetry, so how exactly the symmetry changes with respect to the Fermi gas? Yeah, I'm not sure, but I would say that in this case, yeah, I mean, since there are no scattering events, I mean, it just, just this U1, I mean, at every point, and there's nothing else.
Have people made explicit in these constructions that those marginal Landau interactions actually break the U1 infinity? In terms of not being invariant under?
Okay, well, I'm not aware that anybody has actually checked that. I mean, there's a series of papers by else. I don't think they actually do that, but I think that's kind of implied. So, yeah. So they're more into topology, like, yeah, what are your invariants and so forth. But I think that's basically implied that, yeah, once you turn on interactions, that you will break.
You can probably see it from the Delacreta and Sans paper.
Okay, yeah, that would be a better, yes, yeah, that's probably a better starting point. I agree. Yeah, we should actually take a look at that. Yes. Okay, so let me first remind you a little bit on holography. So yeah, it's the duality between superstrings on ADS and conformal field theory. But yeah, if you take the supergravity or the classical general relativity limit, so then you get classical gravity or supergravity on ADS spaces, dual to strongly coupled large and CFT. And so once you deform the geometry in the interior away from ADS, that means that you deform away from CFT. So you can also model non-conformal or non-quantum critical systems. That just means the geometry is not exactly ADS everywhere, just asymptotically ADS, but in the interior it can be something else. And then, yeah, linearized fluctuations on top of some gravity background will give 2-point correlation functions in QFT. So for example, metric fluctuations will give the correlation functions of the energy momentum tensor. And fluctuations of the fermion will give rise to 2-point correlation functions of or the field theory fermion or condensed matter fermion. In other words, they will give so the imaginary part of this will give kind of spectral function of holographic harvest, so to say. So the first system that people studied was studied by Jan and Kunrad and also by Hong and John. So the Hong called it semi-local quantum liquids, which on the gravity side corresponds to the simplest possible system. Just take a charged black hole with some given charge, which encodes for electron density and chemical potential. And then, the spectral functions usually show non-Fermi liquid peaks. So, yes. So something like this, so very asymmetric. So, and on one side you have a bump, on the other side you don't have anything. So very non-Fermi liquidish in general. Although there is also a regime where you can make these peaks like long living and stable. But I mean, generically, I mean, you get something like this or a mix of stable and unstable, and that corresponds to fractionalized phase. I mean, this terminology, perhaps it's not very much used nowadays, but in the sense that the Ladinger theorem is not satisfied, there's no Fermi surface like entanglement behavior. So it's it looks like that, like in the thermodynamics and in like total charge count, you don't really see your fermions. And the simplest model also has finite 0T entropy, but that can be cured. So this is the so-called Gubzer-Rocha model, which gives you kind of similar behavior of the spectrum, but with zero entropy at 0T. So this this can be cured. And so at best it's something like strange metal. I mean, people even got linear resistivity from this. So it smells a little bit like strange metals. But then I mean, there are things which are not satisfied. I mean, so it probably, I'm pretty certain it doesn't correspond to any realistic system, but it's an interesting, in Jan's word, scaling atlas, which can tell you, so how these thermodynamic functions and response functions and the self-energies, so how they scale depending on the parameters of your model. And so these scaling laws at best might be something more universal. But then this can be unstable to back reactions. So if you add anything else in the bulk, then I mean, this will break apart. So we should look for the true ground state. But before that, I just want to tell that, so what you can do is you can make black holes with corrugated horizons. So with baby horizons like this, and then that gives rise to modulating chemical potential, or in other words, a lattice. So just like you have here, you have a lot of density here, or actually, so here you have a lot of density, then here at the top of the potential, you have little density. So it's lattice. I mean, lattice within a continuum, but that I think is okay. I mean, realistic materials also live in continuous space, the ionic lattice will give, some modulation of the density. And then, that leads to a wealth of new physics. People have seen signs of Mottness, Hubbard-like physics, and so forth. And so as far as I know, the highlight of this approach was, so the fit of measured RPS MDCs to holographic prediction. So this is this paper from Leiden, Utrecht, Amsterdam, Nijmegen collaboration. Although as I learned these days, I mean, the story is more complicated also here. So I mean, there's a wealth of phenomena, not all of which are accounted for by holography. But so at least some of the curves, were fitted successfully. So here I've shown something that, this is something else. So this is from our Belgrade paper, where we try to just fit these, so MDCs from holographic lattices to predictions from the Hubbard model with, so getting Mott-like physics. So with the bulk dipole coupling, and so you can fit it to Hubbard model in the metallic regime. But again, the issue is, I mean, is it anything more than just a coincidence? And now, so from this viewpoint, I don't think it's much more than a coincidence. Or, I mean, it tells you that you are in some very general regime where you kind of see, this sort of, quasi-particles, so which, with weird scaling, but they're still quasi-particles. But I don't think we should interpret it as like describing any specific lattice model or any specific material. And the practical issue with this approach is also that there's heavy numerics, so it's hard to, you can't really see it, but I wrote hard to play around. So it's always nicer when you have some analytic inside. This way, you don't really understand what you did. But perhaps a more fundamental theoretical issue is, so what is the stable ground state? So perhaps that leads us to a Fermi liquid. And this you get by adding fermion here, so to say, in the bulk. So you just add charged fermions, so on top of the black hole. And then, so what happens is that black hole discharges into the fermion cloud. So normally you expect that things will like to collapse into a black hole, but that's true of neutral black holes or black holes with negligible charge. But if you have strongly charged black hole, then there's also Coulomb repulsion. And then it can also happen if that is strong, the black hole, on the contrary, the black hole explodes. It's more thermodynamically preferred not to have a black hole, but something which is less compact, because then the Coulomb repulsion will be lower. So this is like, why this happens. Why we don't have things collapse into a black hole as we perhaps expect, but the other way around. And then, so this is tractable in the Tolman-Oppenheimer-Volkov or fluid approximation. Or so this is the same way that you model neutron stars, only that here the fluid is charged. But basically you just model the electrons as an ideal fluid. So the total action is the gravity action plus electromagnetic Maxwell action plus the action for Dirac fermions. And these are counter terms that you have to get to the ADS boundary, just to ensure that the action principle is that. So this is a formal thing. But so the Dirac action would really be a Dirac fermion in the bulk. But then, the TOV approximation means you just replace it by a fluid action. So U is the fluid's velocity, lambda is the Lagrange multiplier. So just ensuring that, U squared equals -1. And then, rho and sigma are energy and charge density. And this is, so coupling to the electric field. And then this gives sharp, long-living quasi-particle peaks in the spectral function. So I'm not sure how visible this is, but this is K, this is E. And as you see, so there are many. So at every energy, like you find, at fixed K, you will find peaks at different energies, or the other way around. So at given K, you will have, at given E, you will have peaks in different Ks. So in other words, you have a full bunch of Fermi surfaces. And that I think you understand, right? Just the artifact of the fact that the fluid limit. So fluid means that you have that you have filled many levels of your bulk fermion. So we know why this happens, and in principle you could try to move away from large N limit. But for sure, this is also not a good Fermi liquid, even though. So quasi-particle peaks are very stable, but they're actually too stable, because you expect imaginary part of sigma to go as omega squared, but here they're exponentially sharp. So that's, I can imagine that perhaps could happen with some weird interactions. I don't think it's too much of a problem, but it does tell you that it's not, the Landau Fermi liquid, and large N implies, so N distinct Fermi surfaces. But I think the most important of all is that free energy will also scale with this Lifshitz exponent, which is in general so with some arbitrary exponent, and entanglement entropy will also have arbitrary scaling. So this again is something less universal than what we're looking for. Again, as I said, I'm fine if perhaps we can find pristine Fermi liquid, but you certainly expect something with some universality properties. So this is not the case here. Now, if you want to move away from the fluid limit, what people call quantum electron star, it means you have to introduce finite N corrections. In other words, you introduce quantum fluctuations of this bulk fermion. So this was first done by John McGreevy. And his group in 2 or 3 papers in, I think, 2012, 13. But that also, required heavy numerics, and they were actually not able to compute many things. They did everything correctly. we're careful about IR regularization, UV regularization. I mean, and yeah, so they did everything very carefully. But yeah, so the outcome is that the infrared divergence, so yeah, in the interior stays, and you need an infrared cutoff, which cannot be removed. But then that means that you have to cut off the most interesting physics. I mean, that's what we want normally, right? Infrared, like, yeah, the low energy behavior is what we see. So, so yeah, I mean, doing this, I mean, yeah, completely, yeah, so according to following all the rules is just too difficult. So what we tried with, yeah, so with Kunrad a few years ago is to cut corners a bit. So to start with a very simplistic hard cutoff model introduced by Subir long ago, and then yeah, so replace this by soft cutoff. So basically we still keep this infrared cutoff, but it's soft. So I mean, it's not like you completely cut off energies lower than some, say, omega 0, but you just slightly, I mean, yeah, thin them out. And yeah, then you can do more, then you can compute the spectrum, but the outcome is that at low energies you really have just non-interacting gas. So this is like the spectral function. So yeah, so what you can, yeah, so what you, yeah, so the important thing are the blue points. So the red one is just, yeah, so Dirac fermion spectrum. So it doesn't, I mean, then just for comparison, I mean, yeah, this, yeah, so this black curve is basically just to guide the eye. It's a little bit regulated, but basically I can just focus on the blue points. And as you see, there's some gap, and within this gap, you can show that there's always like a Dirac delta peak, which of course you cannot see in the numerics, but it's here. And what's a Dirac delta? Well, non-interacting gas, right? I mean, it's an infinitely narrow peak that you cannot see for this reason. And then outside it, you have this conformal, or if you want, quantum critical branch cut. So this is for, yeah, for zero momentum, this is for finite momentum, and that's like omega k plot. So yeah, the white, yeah, the white area inside is the, yeah, so where this Dirac delta peak will move. And then this is like the, yeah, so the conformal, yeah, how to say it, bat, if you want, so at higher energies. So that's again, so yeah, that's again not what a healthy system should do. I would be fine with having some picture like, okay, I have like free Fermi gas, like some valence electrons or something, which are then coupled to the, but that would even smell a little bit like SYK based models, which are then coupled to, I mean, to the conformal bat. But here there's no coupling. I mean, they're just one or the other. So yeah, it's apparently this approach is very difficult. I mean, so yeah, so yeah, the outcome is that, okay, so you have these semi-local quantum liquids, like something like some strange-ish metal, so which, yeah, which are a nice, I mean, toy model, but not more than that. Then we have these electron stars, which, yeah, which are very weird, and I'm going to talk more about them, and yeah. But yeah, I mean, they're a bit weird because of this, yeah, multiplicity of Fermi surfaces. And then when you want to move away from that, when you want to do the quantum electron star, then I mean, it's really, I mean, then it's super difficult. I mean, after, I mean, I know that John McGreevy, I mean, has spent, I mean, a lot of blood and tears, I mean, trying to do that. And he did it. I mean, he didn't cut corners, unlike us. But it was, I mean, eventually, I mean, you just get a background and it's too hard to perturb it. I mean, we cut corners and also try to do something better than this. But again, so it's so difficult that it's interesting. So why is it so difficult to have a consistent calculation of electron cloud plus black hole? I mean, also from the, if you want GR viewpoint, it's interesting. I'm not aware of any reason, but it almost looks like there's a theorem preventing you from doing it. I mean, there are results, of course, about, yeah, tunneling from vacuum to vacuum and so forth. And I think, yeah, it was argued that you need to start, that it's indeed very hard, like, to perturb away from false vacuum, which is like RM black hole in this case, and move to the true vacuum, that you basically need to guess the true vacuum and then like perturbatively move toward the correct solution. But yeah, so I think that this is an interesting question and should be answered. Is there a problem of principle with doing this calculation consistently? But then also from field theory or condensed matter viewpoint, it also, I mean, yeah, so it's also the interesting issue of, okay, is there something at the fundamental level preventing you from having some stable Fermi surface in holography? And to better understand this, so we decided to study transport in the electron star, which perhaps is, I mean, one of the first things that comes to mind, but somehow, yeah, it was not done before, yeah, like a year or two ago. So yeah, according to holographic dictionary, that means you solve the bulk fluctuation equations. So yeah, fluctuating metric, fluctuating gauge field, and we look at the transfer sector. So we have the transverse and the longitudinal sector. So we decided to look at the transfer sector, well, because it's a little bit easier. We have, I think, 3 equations instead of, what was it, 4 or 5 equations. And so yeah, in the transverse sector, naively you expect a diffusive channel. So something like, yeah, some pole going like d times k squared in the bottom half plane. And then the rest is just technicality. So you have these equations, then you package, yeah, the fluctuating components of the metric into gauge invariant linear combinations, x and y, and then you simplify this a little bit further and you get, yeah, these fluctuation equations. Yeah, so what, so yeah, maybe for, yeah, so for holographers in the audience, I should say that, yeah, that you cannot actually do the final step that you usually do in black hole backgrounds, which is introduce so-called master variables and decouple the equations completely, because here you still have u and y, and here you have y, and I think in this term there should be u. So yeah, you can't actually completely decouple them. Normally you can do that. And you can really see that this is because of these terms with sigma, so with the star density. So it's really like, yeah, having this electron cloud in the bulk makes it also at the formal level more complicated. Okay, and so in a nutshell, yeah, so what we see, I'm going to show the plots now, but let me first tell you. So yeah, we get good diffusive hydrodynamics at low temperatures and at high temperatures, but at intermediate temperatures, there's no diffusive pole and things are more complicated. So yeah, intuitively, this can be understood in the following way. So at high T, we are almost in the black hole regime. And then we know that, of course, yeah, thermal black hole has good hydro description. And yeah, so at low T, we're close to this Lifshitz regime. I didn't mention this, but yeah, so this, yeah, electron star at 0 temperature. So when you back react, when you have this phase with many very sharp Fermi surfaces. So at 0 T, this geometry is the Lifshitz geometry. So geometry with anisotropic scaling of time and spatial directions. So that's called Lifshitz. The scaling exponent is the Lifshitz exponent. And people have studied these geometries a lot, both Lifshitz and the more general version called hyperscaling violating geometries. And these also, I mean, in general have good hydro. So that we also understand that intermediate temperatures, I guess it's just that fermions and both the fermions and the black hole are both equally important. So, I mean, yeah, you can't ignore neither one or the other. And they interact, and that's why you get this complicated mess. So that would be the intuition, that this, yeah, intermediate regime is very really, yeah, you have to take into account both subsystems. So, okay, this is, so yeah, this is the low T regime. Yeah, so maybe, I mean, yeah, so these are just, yeah, so real and imaginary part of the correlation function. Not sure how, I mean, perhaps I should have plotted like, yeah, just the position of the peak or like the motion of the pole in the complex plane. Yeah, maybe, yeah, this is not the best way to present it, but basically if you just look at if you just follow the line along the brightest region, you can see that, I mean, it's some sort of parabola. So yeah, so in this imaginary part, which is more intuitive, so you see that you have some sort of parabola. So this d times k squared scaling. Then at intermediate T, again, look at the imaginary part, but yeah, you can see that you have something very different, God knows what. And then, yeah, so at high energy, yeah, so in this case, you can, yeah, so, yeah, in this case, it's, I mean, a clear parabola. Here, it's not, yeah, maybe it's not so obvious because it's, yeah, so the intensity is not so high compared to the surrounding. yeah, so to the background in the spectrum. But yeah, so I mean, if you plot this as as a bunch of 1D plots, you can also see that there's basically parabolic dispersion. So this is it, yeah. So at low T and at high T, there's diffusive hydrodynamics, but at intermediate T, I'm not really sure what it is. It's something complicated. So, but the most interesting thing and the anticlimax is that there's an instability of the electron star, and that we should really think of, of something that we should now really think of a reason of why this is happening. So you can actually do semi-analytics in the infrared. So you take your equations of motion and then you expand near the near horizon at finite T, or just near at r going to infinity, so at 0 T, and then so you get an expansion where some of the so these coefficients D1 and D2, they're functions of some analytically known and some unknown quantities, and these unknown quantities have to be fit from the numerics. But so it's kind of semi-analytics. But anyways, what you get is this. So that so there's plus D1k term minus D2k squared term. So this is the diffusive term. But since this guy comes with a plus, it means that at k small, you can have a pole in the upper half plane. So diffusion poles exist, fine, they're here. But for small k, this guy will dominate and will lead to a pole in the upper half plane. And as we know, that means an instability. If there's a pole in the upper half plane of a response function, so that that violates Kramer's Kroning, and that so that means that you have that you have an instability, that basically your perturbation will grow indefinitely in time. And in particular, you see that it happens at small k. Starting from 0 k, which is particularly alarming. Like if it happens at very high k, you can always say, well, then I'm outside of the domain of validity, regime of validity of this effective theory. That's fine. At high momentum and energies, your effective theory just doesn't work. But if it happens at very small k's, then it means that it's unstable to arbitrarily small perturbations. You can't do anything with it. And also, this linear term is non-analytic because it's modulus k. And then, it's also very weird. So where does this come from? Because normally, these dispersion relations are always analytic for black holes. So this is something very special for this star. And finally, I should say that at t equals 0, there's no instability. So then this guy drops to 0. So the 0 T electron star is actually perfectly okay. But of course, a healthy Fermi surface, should exist also at finite T, should not disappear. And this is just what so the illustration of what I said. So this is just, the real part along the imaginary omega. And you can see that, in general, also here, on the positive part, you can also see, you can also see peaks. So, just as I said. So, what's going on? The first thing we tried is, maybe it's the pathology of the fluid limit. So included the leading quantum corrections in the WKB formalism. This was done long ago. And then we just, used this formalism, for this calculation. So basically we did WKB corrections of the background, and then we computed the response functions again. But it doesn't help. We did this calculation and and you get the same. So the reason might be that, so there might be some other thermodynamically preferred, perhaps more compact solution of this Einstein-Maxwell fluid system. So electron cloud just wants to go over to that other solution, but we don't know which one. So it's not Jeans instability, definitely, which is the first thing that comes to mind. And I don't know what instability it is and what the solution should be. This, I guess, more or less unique, spherically symmetric static solutions. Of course, you could make it rotate, but I don't know. I don't know, but what it tells you is that we really should do something else. So while 0 T electron star is probably again useful as some sort of toy model, then obviously, you can't get any high temperature physics from it.
What is the geometry of the near horizon?
With electron star, it's Lifshitz. So, but at finite T, it's, I didn't perhaps yeah, I should have shown this, but at finite t, what you get is this. Here. Yeah, at finite t, you get like Rn black hole. And then at finite distance, you get electron cloud. So at finite t, near horizon, you're always just Rn. But yeah, like sum of the charge, so basically, yeah, Q total is, yeah, Q Rn plus Q cloud. So yeah, it's Rn, just Rn, which we know does not have this. But of course, it interacts. I mean, it feels the force is coming from here. So that's apparently what destabilizes it. So okay, back to the basics, back to the drawing room. So what could be some other meaningful approach? So yeah, just hook up theory with whatever like field content, which will satisfy those basic requirements. But then the trouble is that it seems impossible to satisfy them also, as Blaise wrote in an email. So yeah, I don't know of a holographic model that captures everything. Inevitably, it seems like one needs to make a choice which features one insists on keeping. So yeah, we want to have this free energy scaling, entanglement entropy scaling, correct quasi-particle form, zero sound, and it might well not exist altogether. Like the standard choice would be those Einstein-Maxwell dilaton theories. So gravity plus electromagnetism plus this non-minimally coupled scalar dilaton, which basically like influences your scaling and that allows you to have various scaling exponents. But then I mean that will never give you the correct free energy scaling unless you violate the null energy condition, which is kind of consistency condition in GR, and you shouldn't violate it. So END just doesn't seem to work. It can, Gubzer-Rocha is like one subset of this. You can get backgrounds which will give you, say, log scaling of entanglement entropy and other things. But for example, it will not give the free energy. So let's see. So let's see how we can think of it. In a manner of some sort of mean field theory. So the appropriate language for this, I think, is the patch bosonization, which is a very old result. So I'm aware of Houghton and Marston's paper from the 90s. I don't know, probably people tried even before that, but they had a series of very detailed and clear papers in the 90s and early 2000s. And Haldane had several papers in 2000s, then Sansikli some 10, 15 years ago. I mean, of course, every next generation, brings something new, of course. It's not all identical, but it's this sort of approach. And this is related, but not equivalent to this loop group description of Sandhill and Dels and the Vesumino-Witten approach of Luca. The loop group approach is not, they don't really write an effective action. They just want to explain phenomenology in terms of symmetries, but basically, implicitly this loop symmetries is there. And also, this Lucas approach, through this effective Vesumino-Witten model, I think should be secretly, not exactly equivalent for sure, but about the same thing as this patch bosonization. So the idea is divide the Fermi surface into linear patches, so 1 + 1D patches, and then each patch can be bosonized because, of course, in non-spatial dimension, there's no statistics and bosonization always works. And then each of these patches will be a but interaction among the patches will destroy conformal invariance. Okay, so how does this work? You can find the details in, as I said, in Haldane and Houghton and Marston. But so roughly speaking, you start from your fermionic field, and roughly speaking, it's e to the power of phi, where phi is boson. So this is bosonization. So this is, phi is kind of, this effective boson is kind of phase of this fermion. Where so S is the number of your patch, so every patch corresponds to some K on the Fermi surface, and so then you have a bunch of patches or a bunch of 1D systems, so each parameterized now with this effective boson phi. So and then the descendant of this boson in the CFT language is a conformal field of weight 1, 0. Or what does this mean? Well, it means that it means that phi itself has this logarithmic propagator, but then when you take a derivative, which is roughly again this fermion psi, then yeah, the derivative of the log will give you like 1 over this thing. So yeah, it up to this cutoff, like it has power law scaling, and S is the so it is the normal on the Fermi surface. So yeah, like at every patch is just some simple scaling field up to the UV cutoff, of course, which is okay, which has to be here. I mean, of course, we know that. I mean, Fermi liquids are effective things, and so that's what it looks like. And in particular, the phase invariance for psi becomes gauge invariance for phi, because so you can always shift psi by a phase, right? But then for phi, it just becomes a linear shift. So which means that you get a formal magnetic field. It's not physical magnetic field. It's nothing to do with normal person's magnetic field. It's just a very formal thing that you can add, in this effective bosonized action. And this is all just for a single patch. So then you want patches to interact. So the Hamiltonian for the whole Fermi surface is something like this. So you integrate over coordinate space, you sum over patches, which is basically the momentum space. And then you have, this nabla phi is kind of your fermion projected to the, to the unit normal in the Fermi surface. And then, multiplied by some effective interaction potential, which is just, dependent on spatial distance and on momentum on the Fermi surface. And which must have, this component, which is kind of kinetic term, which is just Fermi velocity times, this quadratic contribution here. And then this F is kind of Landau Fermi liquid interaction. And in the semi-classical regime, effectively this patch label or the momentum on the Fermi surface is just a coordinate, so just like X. They commute. So you really should, I really see no reason not to think of S as just another coordinate, for this Hamiltonian. And then, so what would be the holographic dual? So there is actually a supergravity background that has the correct t-squared scaling and correct entanglement entropy. They're just ADS3, because ADS-D will give F scaling as t to the power of d minus 1. So when d equals 3, so that gives t squared. And then similar for entanglement entropy. It has dimensional scaling, and in ADS3, it will have this logarithmic contribution. Of course, just pure ADS3 is just pure conformal field theory, which is never going to give you zero sound, or those other things. But it does have these two scaling laws. So let's think what that means. So we've seen that QFT dual is CFT on a line for every patch. So 1 plus 1 d CFT, but then you somehow have a full circle where at every patch of the circle you have this thing and these interact among themselves. So we need to embed this, so this ADS3 thing with CFT2 dual, we need to embed it into two additional dimensions. One is the additional spatial dimension, if we have a two-dimensional material, so then we want to have two spatial dimensions, and then we also want to have this momentum on the Fermi surface or patch, which I said here is formally a coordinate. So we need basically two additional dimensions. So we need to embed it into something 5-dimensional. Or in general, so for a Fermi surface in these spatial dimensions, we need 2 times d minus 1 extra dimension. And actually, so this, so the space-time which satisfied all of this exists. Of course, it still doesn't mean that it's necessarily a good Fermi liquid. Concerning these last two bullets, it definitely exists. So it's supergravity with Chern-Simons term. So with ADS3 throat in the interior. So this is an old story by Krauss and Doker. So a series of their papers from 2009, 2010. So they do ADS5 with ADS3 throat, but it should work in any odd dimension because of course Chern-Simons requires odd D. And this, I think, also fits nicely. So the fact that you should, for every spatial dimension, you should also add 1 extra dimension of momentum. Basically, to jump by 2, that's really what you get here. Because Chern-Simons is, topological term, which is dependent on, on the dimension of the system and defined only on the boundary. So the field content is you have the metric, you have this U1 Maxwell field, and you have a dilaton. And so the action is Einstein-Hilbert-Maxwell term plus plus boundary term plus Chern-Simons. So this is like Einstein-Hilbert gravity action, Maxwell action, this is, I mean, this shouldn't be here. Sorry, this is a typo. I mean, this is nothing, obviously. So empty integral, sorry. So just ignore this. Then the next term is those boundary counter terms. And then also on the boundary, you have this Chern-Simons thing. But it's Chern-Simons for the Maxwell field. It's not Chern-Simons gravity. There's also Chern-Simons gravity, which is way more perverse. And I'm happy that, I mean, we don't have to have this. I mean, and this is actually so-called top-down action. So it's actually consistent truncation of minimal d equal 5 supergravity, which again comes from 10D type 2b. So basically, yeah, it's I mean, that by itself is of course not necessary for an effective theory, but it's nice in the sense that we have more control. And you only have magnetic field. So yeah.
So wouldn't you get an ADS3 in the IR with some arrangement of higher form fluxes without any Chern-Simons?
Sorry.
Do you actually need the Chern-Simons to get ADS3, or could you also get that from some arrangement of higher form fluxes?
You don't actually. You can just throw away Chern-Simons if ADS3 is all you want. True. But Chern-Simons is there, I mean, to ensure that you don't have gauge anomaly, which I think is important also in our context. It's also there to make it top down. Okay, we don't care about that. But I think to make sure that your current conservation always works properly, I think you need to have Chern-Simons. So, yeah. Of course, whether you could cook up, okay, or you're saying maybe you could also ensure anomaly cancellation with just some higher form fluxes.
I'm not sure that I see where the anomaly is coming from, but I see the bin.
Yes, yes.
I give you the 2-minute mark, so maybe.
Oh, yeah. So then we continue. Yeah. Maybe, yeah, we should continue. Yeah, but perfect. I mean, I'm basically finishing. So yeah, this magnetic field is to be matched to this formal magnetic field that I mentioned. And yeah, so analytic solutions are known and scaling works. So yeah, this is okay, perfect. So then I'm just finishing. So this is, well, that's why I said I only have 15 minutes worth of results. I mean, yeah, this is the only fresh thing that I have, and it's not over yet. So we want to check this. I mean, to check if there's zero sound, to check the spectral function. It's actually an old thing. I mean, the background is basically just there. I mean, you should just compute interesting quantities from it. And yeah, we'll see what it gives. So in any case, yeah, so I want to conclude by affirming what I think Aristo said a few days ago. So definitely, yeah, we should not expect holography to describe any specific condensed matter systems. Instead, it gives like a controlled way to understand general phenomena. So yeah, general laws. So at best, maybe it might provide some scaling laws that perhaps would be sensible to check in experiment, but certainly not more than that. So I think that's definitely true, but I think it's still useful for increasing our understanding, like in general, how these things could work. So yeah, and the question whether there should be classical gravity dual for Fermi liquids or even any stable Fermi surfaces, after all, is mainly a field theory question. I mean, also, of course, a question of finding the gravity dual, but I think it's also, I mean, as I said, the problem that we're not sure of many subtleties in field theory or in condensed matter. And then if yes, I think we definitely should move away from those quantum electron stars because it's so frustrating and it never works. We should understand why, but it seems obvious that it will never work. Instead, we should just think in terms of bosonized theories. So thank you.
I have a question about the fluid description. So what's the main issue with the fluid description? Is it the fact that you can't probe it correctly with the fermion two-point functions?
You mean the pure classical electron star?
Yeah, exactly.
The issue in which sense? You mean the issue in the formal sense or in the sense?
Well, like if you were I don't know, people in nature modeling like neutron stars or whatever, they would use a fluid description and be happy with it. But here,
okay. No, okay, yeah. Okay, so at at 0T, everything seems to be fine. The question is, of course, whether it corresponds to any realistic material. That, of course, is a separate question. Just because it's a form, it's a logically consistent theory doesn't mean it's good condensed matter model for anything. So for 0T, the issue is just that everything's fine, just that probably it's unlike any metal we know of. Whereas at non-zero T, yeah, there's the issue that it's not stable. It's not the true ground state. And okay, now you're asking why when we know that neutron stars do exist at finite T. Well, because it's so, okay, there are two differences here. First, it's charged. Second, it's in ADS. But from the equations, I can tell the issue is being charged. The issue is not ADS. If anything, ADS should make it more stable, like giving the confining potential. But it's really the charge, because it's really this term in the equations of motion, where you multiply the charge of the electron cloud by this perturbation, whatever. So that will be absent for a neutron star, and it's really this term that gives rise to the non-analytic module K term, which in turn gets this positive coefficient. So it's really being charged. That gives rise to some instability. Which one I'd like to know, but for now I don't know.
Any further questions? Okay. If not, let's thank Mihailo again.
Thank you.